after having introduced ourselves to the concept of Fourier integral and Fourier transform, now let us look at the points of comparison of the spectra of a periodic signal and an aperiodic signal. So, if you had a periodic function of time, say a period t naught, then you have an amplitude spectrum magnitude spectrum C n and a phase spectrum as you recall. The magnitude spectrum is an even function of n and the phase spectrum is an odd function of n. So, this x axis can be graduated in terms of frequency n omega naught or in terms of n. Now, a particular C n here and the corresponding phase together, these two components together will give me, that means this specifies the magnitude, this specifies the phase. So, it is C n e to the power of j phi n e to the power of j n omega naught t. So, the significance of these two terms, one specifying the magnitude, the other specifying the phase, is C n e to the power of j phi n is the coefficient of this exponential term e to the power of j n omega naught t. Likewise, for the negative value for this n, you will have these two terms together will give me the conjugate of this, because when C n and C minus n are related by the conjugate relationship. So, this will become C n same magnitude e to the power of minus j phi n e to the power of minus j n omega naught t. So, all these four put together, that means this magnitude and the phase together will give me 2 C n cos n omega naught t plus phi. So, the meaning of this negative frequency minus n omega naught is only, it means that this is the exponent, this is the coefficient of this j t term in this exponential representation. Even though the frequency is negative, these two terms together combine to provide you with a real frequency of n omega naught t, n omega naught. Now, this is the line spectrum and there will be frequency components present only at discrete values along the frequency axis, and they are all integral multiples of the fundamental frequency, and as I said, the spacing between two lines is omega naught. Whereas, when we have got the, this is the periodic case. In the aperiodic case, we have some phenomena which lasts only once, it does not repeat itself, the period t naught tends to infinity, and we said this will lead to a spectrum which is continuous, and we call that coefficient density f of j omega naught magnitude, and we also have associated with this, after all f of j omega naught, f of j omega in general is a complex number, is a complex function, therefore, you have magnitude and a sign. So, you have also an angle associated with that, which is a continuous function. This is argument of f of j omega, which we may call phi j omega or phi omega. Now, we said this coefficient density, what does it that really mean? If you take any small interval delta omega and the corresponding here A12. This slice of the spectrum of the two spectra, the magnitude spectrum and the phase spectrum together, these two will imply a constituent of your f of t. What is that function? F of j omega magnitude, this is the coefficient density. That means over this interval of frequency, the density at the center is f of j omega. Therefore, the total magnitude is f of j omega magnitude times delta omega. It has a phase e to the power of j phi omega, and then the exponential representation of function of time is e to the power of j omega t. So, this magnitude and this phase together will give rise to this function of time. Naturally, on the other side, corresponding to, if this is omega, this is minus omega, and again if you take two sections of the spectrum of width delta omega, these two together will give me f of j omega magnitude times delta omega times e to the power of minus j phi omega e to the power of minus j omega t. So, this portion of the spectrum combined with this portion of the spectrum, these two together, if you combine these two, you will get 2 times f of j omega delta omega cos omega t plus phi omega. So, you have, even though you have components corresponding to negative frequency, what it really means, for every negative frequency here you have a positive frequency, and all together will yield a real function of a cosine term. This is magnitude, of course. And you have a frequency at every point. In other words, what we are having here is not at any given if you have a periodic case, at any given point of time, at any given point of frequency, if you want to know what is the amplitude is 0, vanishingly small. But if you take a small width along the omega axis, and if you consider this entire slice to be representative of one single frequency term at the center, then the amplitude of that particular exponential term will be given by this. So, this is called coefficient density. So, in other words, if f of t is in volts, if f of t is in volts, the dimensions of f of j omega is in volts per cycles per second, or dimensions will be volt seconds. Whereas, in the periodic case, if the f of t is in volts, Cn will be in volts. It gives the amplitude of each individual component, whereas here it gives not the amplitude, but the magnitude density. It is something similar to what you know in your applied mechanics courses and so on. We have a beam here, we have concentrated loads at point, this is one way of looking at it, and then sometimes you have distributed loads. In the case of distributed loads, what you say is so much kilograms per unit length. That means at any given point there is no load, but if you take a small interval, and the total load in that interval will be the density times the small elemental distance. So, similarly here you have a situation where each individual frequency component is almost negligible amplitude, but you have a over a small interval of along the omega axis, you can think of that these sections of the spectrum to represent a function of time which has an amplitude which is f j omega times delta omega. This is the density, this is the total amplitude. So, what we have done is to demonstrate by taking the limiting case of the Fourier series as the frequency becomes smaller and smaller and as the period becomes larger and larger, that even an aperiodic case can be thought of as composed of number of different frequency components. In contrast to the Fourier series which concerns itself with the periodic case, here we have a frequency component at every conceivable frequency, all along the omega axis from minus infinity to plus infinity in the exponential representation, but their amplitudes are vanishingly small. So, the amplitude at any given frequency is 0, but over a small width you can think of an amplitude. So, what we are really talking about is the amplitude density or the magnitude density, otherwise called coefficient density, and that coefficient density is, we term it as f of j omega because it is a function of omega and we would like to associate j with that term omega, therefore, it is f of j omega. So, we have basically these two relations which are important, which we will use for our further work. The coefficient density f of j omega is obtained from, you are given f of t as the integral from minus infinity to plus infinity of f of t e to the power of minus j omega t dt. This is the coefficient density which we call the Fourier transform. And once you have the Fourier transform, we can recover the time function f of t by writing an integral relation from minus infinity to plus infinity of f of j omega e to the power of j omega t d omega. Both integrals run from minus infinity to plus infinity. In one case we get 1 over 2 pi here, in the other case we do not, and as I said, we use this, we get this 2 pi because we are defining the coefficient density as the amplitude per cycle per second, f naught instead of omega naught, and this is called the Fourier integral. That means we are, you always look at this as f of t is being composed of an exponential term, the function of time like this, and what is its amplitude? F of j omega is the coefficient density delta omega over 2 pi. So, this is the amplitude. F of j omega is the coefficient density. So, at this frequency, if you want to look at this, you take a small interval along the omega axis. So, delta omega over 2 pi, this is the base, this is the amplitude density, therefore, this is the amplitude, and take the limit as delta omega goes to 0 over all possible frequencies and summation over all possible frequencies, and that leads to this integral, right. So, what we have done in this lecture is to say that any aperiodic function can be thought of as an infinite summation of elementary frequency components, each with a vanishingly small amplitude and with all frequencies present along the omega axis. We will continue the next class, next lecture, discussion of the properties of the Fourier transform.